Hello there and welcome to this final video lesson or video demonstration of the mid-year exam and revision. Using this more or less as a memorandum. This is now question 3, the Euclidean geometry, and of course Euclidean geometry is one of the most difficult sections for the students, and for one simple straightforward reason: you don't know your theorems. So nothing I can really teach extra on this topic except to show you how we use our theorems in solving all of this. So the first question was question 3.1. In the sketch below, A, B, and AC are tangent lines to the circle with center O at B and C respectively, and prove that angle A1 is equal to angle A2. So this proof is very similar to the proof for showing that AB and AC are the same length, and we do that by, and we said there even you may use constructions. So that's basically a hint to use constructions. So the first construction is just constructing the lines. What's happening? There. Okay, constructing the lines here are which are our radii connecting OB. So that is our construction. So I'm not going to write it down. Let me do construct line OC and OB. Okay, and then after that, then I'm going to prove that these two triangles that I've now created are congruent triangles, and because they're congruent, that means A1 and A2 is equal, ACO. Okay, so in those two triangles, so when I want to show something is congruent, ideally I would like to show that all three side lengths are equal, and that would be one way, or there's a few different ways. So let's see which one I'm going to do. So first of all, I can just say, well, AO is equal to AO. That's common side. Secondly, I can say OB is equal to OC, and they are radii of same circle. And then finally, I could say that AB is equal to AC, tangents from a point, tangents from common point. Or, so that is, if I did this, then I would say, well, triangle ABO is congruent to triangle ACO, and my reason would be side, side, side. Now that's technically the most strictest definition of congruence, but I could have also said, instead of this number 3, I could have said instead that that angle OBA is equal to angle OCA is equal to 90 degrees because the radius is perpendicular to the tangent. Okay, and then I could have said, well, triangle ABO is congruent to triangle ACO, and the reason why is this time, so I've got both of those, this time is I've got a side length and the hypotenuse. So it's the hypotenuse, it's not AB that I used. So I could have said that the reason is I've got a 90 degrees hypotenuse, because this is the hypotenuse that's common, hypotenuse and another side length. And so those are the two ways you could have proven the congruence of those triangles. But I'm not done, because that wasn't the question. The question wasn't to prove they're congruent. The question was to prove A1 is equal to A2. Therefore, A1 is equal to A2 from congruence. Or you could have just quoted this again. Okay, so that's it. It's the first question. Second question. In the diagram below, we've got these angles ABC, DEF. Prove that these triangles are similar, thereby proving the theorem that equiangular triangles are similar. So in other words, equiangular triangles are similar. When I have two triangles with the same with equal angles, then they are similar triangles. So the proof here requires a construction as well, and that's the most difficult part of any of these proofs, is just remembering the construction. And in this case, the construction that we should remember is to construct M on DE so that a DM is equal to AB, and N on DF, let me write it out so that you can see we have enough time, on DF so that DN is equal to AC. Okay, and so once we've done that, so we've got a point here, the point M, we've got a point there, the point N, and when we connect this, we have that these two are equal, and this one is equal. That's the point. That is my construction. Now this is going to rely on kind of three parts. I want to show that, first of all, that these two triangles are congruent. Then when they're congruent, I can prove that MN is parallel to EF, and after I've proven that that is true, I can use my proportion theorem to show that this portion over that portion is equal to this portion over that portion. That is my proportion theorem. And because DM is equal to AB, I can just substitute, and I've proven my point. So the first point I'm going to do is the first step is in triangle DMN and triangle ABC. We have that DM is equal to AB, construction. Then we have that DN is equal to AC, construction. Then we have that D is equal to A, given. That was what we were given in the beginning. All these angles are equiangular. So we know that this is equal to that. And so I have two sides and an inclusive angle. Therefore, triangle DMN is congruent to triangle ABC. Side, angle, side. Very important that the angle is between the two sides when I have two sides and a triangle. Okay, once I've proven that, I can move to my next step, where I can now say, well, therefore, angle M, let's number that, and so use a little bit darker color. So we have a 1 and a 2, and we do all this on our diagram sheet that you were provided with. So therefore, angle M1 is equal to A from congruence, but sorry, not A, B, it's equal to B, but B is equal to E, given. Therefore, M1 is equal to E. Don't forget your cuppies. Okay, so this just follows the law of excluding the middle. If M1 is B, but B is E, then I exclude the middle, and M1 is equal to angle E. Now from here, we can now move to show, therefore, MN is parallel to EF. Okay, because corresponding angles are equal. Okay, corresponding angles are equal. Now we have that these two lines are parallel, and we can therefore conclude, we get to our second step, that That means that dm over de is equal to dn over df. And this is the proportion theorem. Okay, and then finally, using this, therefore I can say that AB over DE is equal to AC over DF. Why can I say that? Because of the construction. Because of construction, AB is equal to dm and AC is equal to dn. And there I've proven it. I've proven that, so when is something similar? Something is similar when its sides are in proportion. Its angles are equal and its sides are in proportion. Okay. So there was just another, and this is, once again, this is a proof you must just know. There's only 4 of them in grade 12, and you will get one of those 4 in your mid-year exam, and in your prelim exam, and in your final exam. So know your theorems and their proofs. Okay, let's move on. We're moving to the next question. In this question, we are told, in the diagram below, JD is a tangent. Oh, brilliant. JD is a tangent to the circle O. Also that E1 is equal to E2, A1. So in other words, it's given that E1 is equal to E2 and A1 is equal to A2. And that O is the midpoint of JD. So O is the midpoint of JD. So if I just put all of my information in my sketch, that will just be helpful. I know that this length is equal to that length. This length is equal, or this angle is equal to that angle. This angle is equal to that angle. And I can move on. Prove that JEO, that's JEO, this triangle, is similar to DOA. DOA. So that angle D is equal to J. Angle O, E here is equal to angle O there, and angle O here is equal to angle A there, A1. Okay, so let's see. We must prove, so in triangle JEO and triangle DOA. OA. Now we just have to show which angles are equal. All I need to do is what my previous theorem stated. My previous theorem stated that if I can show that these ones, his angles are equal to those ones' angles, then they must be similar. And so let's see, what can we say? So we already know that A1. Okay, let's use our tangent line theorem, because that's how we're going to get in there. So our tangent line tells me that the angle between the tangent and the chord is equal to angle in the opposite segment. So this one is also equal to that one. Okay, and since those two are equal, I already know that E1 is equal to O3. So let's start with that one. So let's start by saying, well, E1 is equal to E2 given, but E2 is equal to O3, which is the tan chord theorem. The tan chord theorem. The angle between the tangent and the chord is equal to the angle in the opposite segment. So that's my first one. Therefore, E1 is equal to O3. Okay. Now the next one. Can I prove? So let's again use the same. It's the same rule. So this time I'm just doing it on the opposite side. Here I have that O1 is equal to tangent and chord, the angle in the opposite segment. There. And those two are equal, given. So it's the exact same argument. A1 is equal to A2, given. O1, and O1 is equal to A2, tan chord. Therefore, O1, again, law of excluding the middle, A2 cancels in a sense, and then those two are equal. A1. So I've already shown that angle E is equal to angle O, and now I've shown that its angle O is equal to that angle A. So so now the third angle, 1, 2, 3, angle J will just equal angle D, because it's the third angle of a triangle. If two of the angles are equal, the third one is found by subtracting the other two from 180. So if I'm subtracting the same values, I'll get the same answer. So that's just true, and so our conclusion is that JEO is similar to DOA, and that's side angle, sorry. Angle. Great stuff. Okay, so next question. Prove that JE times DA is equal to OJ squared. JE, that side, over DA, that side, is equal to OJ squared. So OJ squared. So remember, OJ is equal to OD. So what we could do is we can start. Notice that this type of question of multiplying side lengths and getting other side lengths multiplied or squared always will follow a question about the similarity of two triangles. If it doesn't, then you first have to prove the similarity of those triangles. Just notice here the amount of marks you get for this question. Isn't it fantastic for the little bit of work that you had to do? But anyway, now prove that. And again, it just follows, especially because it's only 3 marks, it just follows through the application of similarity there. So what we could do is just start with and saying, well, JE over JO is equal to, and now we using the first two and the first and last, is equal to DO over and DA. But this just comes from the fact that JEO is similar to DOA. That's where it comes from. Now that we've shown that, we just multiply both sides with a JO as well as with a DA. So on this side I get DA JE is equal to DO JO. Dojo. Okay, and then we see JE times DA, JE times DA. Now something's odd. DO and JE. Oh yes, DO is equal to JO. So DO is equal to JO, which times JO is squared, because DO equal to JO was given. Why? Because O is the midpoint of JD. And there's it. That's what we had to prove. So silly, I know. Okay, then came a really difficult one. Okay, so this one was overall fairly complicated. I didn't like this question much, but yeah, it's what we have. Okay, in the diagram that they give us, N is the midpoint of KC. Okay, N is the midpoint. BM is equal to MC, so this is also a midpoint. Okay, so this is a midpoint, that's a midpoint. It is also given that AD has a perpendicular intersection with BK at H. So AD intersects DH perpendicularly at H. And that's it. That's the information given. And so, since N is the midpoint of KC and M is the midpoint of BC, according to the midpoint theorem, what can we conclude about MN and BK? So what can we conclude about MN and BK? That they are parallel. That's all we asked. Okay, so let's just get to that question. So BK is parallel to MN. Okay, so let's put it in. Every single question in grade 12 leads you to the final question. So it gets more and more difficult, but the intention is to help you with the most difficult question later on. So that's the first thing you have to conclude. Hence, that means use this fact that you just showed and show that ME over MA is equal to NC over NA. E over MA. So we know that this line here is parallel to that one. ME over MA is equal to NC over NA. NC over NA, well, ME over NA is NK over NA because there's a triangle. Okay, so question 2 here is that ME over MA is equal to NK over NA. Why? Because it's the proportion theorem. The proportion theorem because EK is parallel to MN. We showed that in the previous questions. EK or BK, whichever one you use, they're both lines. Okay, but Kn is equal to NC. That's given. They told us that these two are equal and that those two lines are equal. So therefore ME over NA is equal to, and then instead of Kn or NK I can put NC over NA. Okay, that part is proven. Again, not too difficult. If H bisects BAK, so in other words, if AH bisects, so it cuts this one and that one in half. Okay, prove that H is the midpoint of BK by proving that those two triangles are congruent. Another congruence. Again, I'm telling you what to do. Okay, I'm showing. So how do we start that? In triangle. So remember what the information that's now given. We're giving that these two angles are equal. So in triangle AHB and triangle AHK, the first thing we know is that A1, let's name that one 1, A1 is equal to A2. Okay, that's given. Then 2, we know that H1, let's call this one H1 and that one H2. H1 is equal to H2 given. Okay, it's equal to 90 degrees. Again, that is just given. And then finally, we know that AH is just equal to AH. Common side. And so our final response is then, that means that AHB is congruent to AHK HK, and the reason why is because we have an angle, and one side in common. That is a third way. So now we've actually seen all the ways of proving triangles are congruent, and just showing you how important it is to be able to do so. The next question, now we're not done, because they asked us to prove that H is the midpoint. Now if I've proven that these two triangles are similar, it means therefore it means that BH is equal to HK from congruence. So what have I proven now? I've proven that this is the midpoint of these two lines, BH and HK. This is again the midpoint. And remember, this is also the midpoint. So once again, I now have the fact that this is parallel to that. Okay, so keep that in mind. If H, hence prove that Cn over Na is dH over AA. So if I go to my sketch, that dCn over Na is equal to dH over AA. Cn over what? Na is HA over H dH HOA over dH. So oh yeah, because this is the midpoint and that's the midpoint, so I'm working in these two triangles. Okay, there we go. So I'm working in those two triangles. This is the midpoint, so this line is also parallel. That line and that line, that line and that line. So to prove, I'm going to work up here to prove, and the one thing I hate about these is I kept forgetting CNNA and DHHA. So CNNA and DHHA. There we go. That's to prove. Okay, so I can't use this. I have to prove this. So Cn over Na, that's that triangle. Cn over Na. Let's just see. Cn over An is equal to Me. Is that useful? Let's see. Oh no. Okay, no. So look at this side. Look at this side. DH and so DH over HA. I'm in this triangle here. This triangle here and that triangle. Okay, there we go. Okay, so DH over HA is equal to how much is it? Yeah, DH over HA is equal to NC over NA. No, that just follows. That's just prop theorem, proportion theorem, because HN is parallel. Oh, I suppose that's why. Okay, it's just 2 marks. I should have read how many marks it is. Now I've spent so much time thinking about this. Okay, why is this true? I should have probably first just H is midpoint. let's just say HN is parallel to BC. Why? Midpoint theorem. What is the midpoint theorem? What midpoint theorem just states if I have the midpoint of one side connected to the midpoint of another side, then the two sides are parallel. Okay. Then that's what we saw in question 1. Okay, last question. I think it's the last question. No. If HM is parallel to KC, prove that. If HM is parallel to KC, if HM is parallel to KC, okay, we know it is because it's midpoint to midpoint. If HM is parallel to HC, I shouldn't have put if there. Prove DH over HA, DHHA, MDMC. Okay, so where do we have space? So DHHA, MDMB, DHHA. I don't have space anymore on this page. A little bit here. Okay, so prove the DHHA is equal to MDMB. Okay, let's see which one. DHHA. DHHA is MDMB. Okay, MDMB. What triangle am I working in? So here's a triangle. There's a triangle. MD. AE ME DH. I don't think we've done MD. Well, let me just make sure I've got the right. MDMB DH HA. Let's see. Okay, that is DHH. Just struggling to find the triangle that we're working in. Oh, and let's just remind ourselves what the question gave us. If HM is parallel to KHC, so HM parallel to KHC aha, okay, here we see. Here we go. Okay, I struggled to see the triangle. Here's the triangle. Okay, here's the triangle that we're working in. Okay, so here we have the DH over DA is, so this DH over DA is equal to MD over MC. But MC is equal to BM given. And so then we get that. And for lack of space, oh no. Let me do this. So DH over AH is equal to MD over MC. Great. Oh, this is an incredibly long question. Well, question 3.4 is long. Okay, let's do this last question. It's going to take us, give us 5 marks. It's probably the most difficult question in the whole question paper, but hence prove ED is parallel to AB. So we have to prove that ED, this line here, color it, not with that color, ED, this line here is parallel to AB. And so how can I prove it? Well, all I need to do is, in this triangle, prove that DM over BD is equal to EM over AE. Okay? And it is really just a putting together of everything that I have shown at the top. So first of all, we already know that MD over MC, so MD over MB, sorry, I wrote that wrong, MB over MC. So instead of showing this over that, I'm going to show this over that. So let's rather just extend this. Okay, extend this is equal to this over that. Okay, so let's get on with it. So first of all, I know that MD over MB is equal to MD, it's MD over MB is equal to DH over DH over HA. This was from the previous question, 3.5.4. Okay, but then DH over AH is equal to CN over NA. Okay, but that is equal to CN over CA. That comes from question 3.4.4. And then, but CN over NA is equal to ME over MA. ME over MA. This comes from question 3.4.2. And that's exactly what I wanted to prove. That MD, this portion divided by that portion, is equal to ME over MA. And that's what I've proven. And so I can conclude, therefore, what is it? The conclusion. DE is parallel to AB. DE is parallel to AB, and that's the inverse proportion theorem. Okay. Well, thank you very much for watching. We have done this in, how long did it take us? 38 minutes to complete 38 marks. So that leaves us 38 times 1.2 with about another 7 minutes that I could have used to go back to previous questions and test my answers, etc., etc. Just showing you that there is, once again, more than enough time. If you just quickly go through the type of questions that we got and what you should have gotten just by knowing your proofs. 6 marks plus another 6, 12 marks were marks awarded for bookwork. So yes, this is a little bit different proof than the proof you have to know in your books, but the concept is exactly the same, and many people did get it that. So that one is not too bad. But this one, I don't know how many students got it. Very few, and it's bookwork. It's proof in the textbook. This is very straightforward. 7 marks. So in other words, 20, more than 50% of the marks, 20 marks, were very straightforward. This was simply proving angles, and if you indicated it on here, you got 20. This is straightforward application of that. That's 23 marks. Just, this is so common, proving the two triangles are congruent, and then applying that, not congruent, similar, and then applying the similarity to find an expression. Now here, yes, okay, let's say you didn't get any of these marks that for this really difficult complex sketch. It was a complex sketch, I agree. It's probably more complex than you will find in your final exam, but yeah, so notice just 23 marks, 22 marks I mean, was really straightforward, easy book application of bookwork. More than 50% of this paper is exactly that. So thank you for watching, and we'll see you in the next time we do a memorandum, which is probably for control test 3.